There is a revolution coming. There's a revolution coming with respect to energy, how we think about, how we create, and how we use electricity in our daily lives. And I'm here to tell you about that revolution and tell you what the scientific community is doing about it so that we thrive in it. We not only survive the revolution, but that we thrive. And where I'd like to start is that word revolution. As I was thinking about putting together this talk, what images come to mind when I use that word? We think about the Bolshevik Revolution or the French Revolution or the American Revolution. And I really want you to think in your mind's eye, what does that word bring to mind? What kind of imagery? And then ask yourself, what images can apply to today if there were a revolution in our society today? What would bring you to your knees in a public place? When I say that, what do you think of? A terrorist attack? A bomb going off in an airport? Smoke? Fire? Gunshots? What I'm here to tell you is what will bring you to your knees is what you see in this picture right here. About 3 weeks ago, I took this creep shot in the Denver airport. And I wish you could see the shots after this, the look she was giving me. But if you look closely at this picture and you notice, first of all, she's trying to get some electricity to charge her battery. And look closely at the picture and you see a custodian coming by and she has that look. We've all had that look. Yes, I'm sitting on the floor right next to a restroom charging my phone. Why? Why is that? Where is this revolution coming from? All of us have experienced the anxiety of a low battery on our phone. And I'm sure you could experience it just by seeing that picture. I know I do. So what I'm really saying is, it's not that the revolution is coming. The revolution is here. We are tethered to a battery for our daily existence. Why? How did this happen? It's quite simple how it happened. In my lifetime, we started with a telephone that looks like the one on the left, with a dial and a wire that goes into the wall. Well, now the telephone is so much more than that. It's everything. It connects us to the world. It connects us to our parents and our children and our spouses. It connects us to our coworkers. You know, imagine not being able to send that email when you wanted to send it. Imagine not knowing the latest update on the Kardashian family. Just imagine that. How stressful that could be for you. In fact, I would predict right now that every single person in the room knows the charge on their phone within 10%. What does that tell us? It tells us the revolution is already here. We need the battery. We're tethered to it. Now, compared to the telephone, what's happened in my lifetime with respect to the battery? This is a little bit of an exaggeration, but with a 9-volt battery, I can buy almost the same battery today at Walgreens that I could buy when I was a child. It has not progressed like the telephone has progressed, like the computer has progressed. Now, this revolution, you can feel it. I could tell by your laughter that the emotions are there when you feel the stress and anxiety of a low battery. But what I'm here to tell you is the next phase of that revolution, what is going to happen. And I'm going to describe for you what happens with the electricity grid. That is an on-demand product. You might have heard those words before. I'm going to tell you with respect to electricity what that means. The grid was built over 100 years ago in a very simple fashion. Electricity was produced in a coal-fired power plant. It was transmitted over a wire and delivered for use. Now what that means is, and I'm not kidding you, every time you turn a light switch on at home or turn on your television or plug in your computer, there's someone somewhere, and it might be a computer or a human, turning a knob up. It is truly an on-demand product. Think in your mind, compare that to buying shoes. Imagine if you went in a shoe store and the shoe was coming off the manufacturing line the instant you went to go buy it. There is no other product I know of that is as on-demand produced as electricity is. Think of Zappos. Right? Zappos enables us to have a place where we can store all the shoes in one place before we buy them. And as the grid is progressing, what's happening is it's becoming much more complex. There are new ways to create energy, create electricity from the sun and the wind. There are new ways that we use it in the form of electric vehicles and other devices in our homes. And every one of those new ways actually needs a battery because of the fact that electricity is an on-demand product. I cannot go and turn up a knob to turn the sun up or turn the wind down with how much we need electricity on a day-to-day, hour-to-hour, minute-to-minute basis. So what that means is we need a warehouse like Zappos has We need to think of it like a digital video recorder. We need a place where we can store our electricity and consume it at our convenience later, just like we do with television today. So even though you might feel the stress and strain of a battery problem associated with your phone, what I'm here to tell you is that problem is going to be much more significant in the future. It might be a generation away, but imagine feeling that stress of a low battery with your phone and applying it to your ability to get from one place to another in an electric vehicle, or worrying about, do I have enough power in my home? That is coming for us, but there's an even bigger picture, and that is in places in the world where they do not have the luxury of a grid like we do. So there's an opportunity to solve a first world problem, create better phones, electric vehicles, a more substantially stable grid that allows renewables to come onto the grid. But at the same time, we'll be solving a third world problem and creating an opportunity for people to create electricity, store it, and use it at their will. And you can see, even in the little quadrant here that shows the African children studying, they're using an energy storage device. It's an old one. It's a plank of wood that they're burning and using the light from that. So imagine if we could modernize that in the third world at the same time we solve our first world problems. That is the revolution I came to talk to you about. Now, I am grateful to have led a proposal that won a giant project that is a consortium of great scientists and engineers across the country, about 140 of us, and now am helping lead that project. So what I'm going to do is translate that macro problem that I just described to you into the micro world that we operate in, the ether that the scientists and engineers operate in. And I want to explain to you why it is that we think we can drive this revolution in the right direction. And I'm going to start by explaining how a lithium-ion battery works. And I meant to tell you, it's like, if any of you have gone scuba diving, get ready for a deep dive. I hope I don't give you the bends. I gave you the big picture up top. I'm going to do some deep dive into science, and I promise you, in just a few minutes, I'm going to pull back out, okay? Here's how the lithium-ion battery works. When you charge your phone or your computer or your electric vehicle, you actually dissolve ions in a liquid. And those ions move from one side of the battery, the cathode, to the other side of the battery, the anode. They move back and forth. It creates chemical reactions. It creates difficulties in the materials surviving for any length of time. And you all know this. Everyone in the room here knows how long a lithium-ion battery lasts. In 2 to 3 years, your laptop computer, your cell phone, the battery starts to die. You can't hold a charge. It's because you're moving this matter around. Remember this, please. This is one thing I want you to remember from my talk. You're performing a chemical reaction in your pocket every time you carry a phone with you. And you're moving matter around. Now, what does that mean? I'm a Midwesterner. Here's what it means to me. I'm a bowler. I think you have to be a bowler if you're born and raised in the Midwest. My wife and I are on a couples team. It's a lot of fun. And I was thinking, how do I describe this? Imagine the object of bowling is to roll that ball down like Walter Sobchak or Walter, whatever his name is in The Big Lebowski. Roll that ball down and knock down all of the pins. Imagine for a second if the object of that game, instead of rolling the ball down the alley and knocking down those pins, was to go through the pins and then stay right there and not knock down a single pin. I hope you're thinking, Jeff, that's impossible. And guess what? When the first lithium-ion battery when research was being performed at Exxon in the 1970s by Stan Whittingham, he was told it's not possible to move a lithium ion in and out of a solid-state material. It's the same problem. So this micro problem that we have is to design a better set of bowling pins, design a better lane, design a better ball so that that battery can last forever and hold 5 times the energy, cost 1/5 of what it costs today, so that we can enable this revolution to serve our needs. Now, what does that mean? At Argonne National Laboratory, just a few miles east of here where we're talking, I'm going to describe for you how we get to solve this problem. We have something called the Advanced Photon Source, which is a synchrotron. We spin electrons around this ring that you see here at nearly the speed of light. And when you move electrons that fast and bend them instead of going linear, they spew off high intense X-rays. And as a scientist, I can tell you that really jazzes us up. You feel jazzed? Those X-rays are exciting. They're really intense. They're 1 billion times more intense than the X-ray machine at your doctor's office. And this is the translation I'll make for you. Everyone here knows X-rays. Madame Curie figured this out a long time ago, one of the very few people in the world to win 2 Nobels. We've all had things x-rayed. Well, what happens is x-rays scatter off matter in different ways, and you can see bone density versus flesh versus tumors. And it's been an incredibly helpful tool to humanity. Now, with these super intense x-rays, what we can do is we can go way, way down. And we can see the difference between manganese and cobalt. We can actually see the atoms in action while they're moving inside of a battery. That's what's so important about those intense x-rays. Now, here's another great big tool that we have, supercomputing. This is called the Mira. It's one of the top 5 fastest computers on the planet. It's at Argonne National Laboratory. It does 10 quadrillion calculations per second. You feel excited? Do you feel the excitement of the 10 quadrillion calculations per second? I do. Only because I had to think about what that means. It sounded like some made-up words to me until I really started to think about it. Your typical computer at home on your desk would take you 20 years to do that many calculations. If we took every human being on the planet and had them do one calculation every second, 24 hours a day, it would take 2 weeks for 7 billion people to do that, and what can be done in a second on this computer. Now, so what? What does that mean? It means we can design matter. You see these images here. We can, by understanding very deeply quantum physics and quantum chemistry, we can program this computer to predict a material's behavior before we synthesize it. Now, let me translate that for you. And again, I guess I go back to my Midwestern roots, and I think about delicious baby back ribs. And how, imagine, just think about the tangy, sweet, spicy flavor of baby back ribs. And for my vegetarian friends in the audience, this is a rack of tofu, okay? It's still tangy. Can you feel that? We're getting close to dinner. Delicious. Now imagine if you're a connoisseur and you want to make a lot of ribs. Imagine if you want to try different recipes. And let's say you have a book of 1,000 recipes of ribs. How long would it take you in the kitchen to try every single one of those recipes to decide which one to make for you and your friends and your family? What the supercomputer lets us do is in a moment, imagine in a moment if you could understand the taste of every one of those 1,000 recipes and pick the top 3 to make for your friends and family. That's what the computer enables the scientists to do. Okay, so we've got the great big challenge to work on that excites us. We've got some great scientific tools that have just been developed in the last 15 years. Now, how do we invent? I hope everybody knows the legend that is Thomas Edison, that he only slept 4 hours a night. He was a genius. He had amazing drive. He invented the phonograph first, then the light bulb later. And he was a singular genius. And what I'm here to tell you is some of the stories of Thomas Edison are just a myth. We love to tell the lie to ourselves that one person can go inside of a garage and invent something that changes the world. And in reality, Thomas Edison at one point had well over 100 engineers working with him, and he was a slave driver. You can look this up when you go home at Google and see exactly what I'm talking about. So my point is, why do we need 140 scientists and engineers to develop the next best battery to help us with this? So let's talk about teamwork. We have here Jay Cutler, the quarterback of my beloved Chicago Bears. So imagine if instead of Jay Cutler, we had the Thomas Edison of the NFL running the team. So we have, thank you. We have Peyton Manning running the team, the Thomas Edison of the NFL. But how do we build the team? Let's go through some genetic engineering and let's copy him. And let's build an entire team full of Peyton Mannings. Can you imagine how exciting that would be? Think that through. It would be the best team ever until you actually start to think about it. Has anyone here ever seen Peyton Manning try to run the ball or throw a block? He's terrible. It's like his feet are made of cement and glue. Why? Because he's trained his whole life to be a quarterback. The running backs have trained their whole lives to be running backs. The linemen to be linemen. The defensive ends to be defensive ends. It is the same thing in the world of science. Why would we think it's anything different? We need physicists, chemists, chemical engineers, mechanical engineers, electrical engineers. We need computational folks. We need experimental folks to be able to do what we need to do to build that better set of bowling pins. Okay, so we've got the great big challenge. We've got the outstanding scientific tools. We've got a world-beating team. I haven't even told you yet the most thrilling part of this experiment, of this project that we're doing, and that is that we might fail. We have the best scientific tools in the world. I would say we have the best team in the world, and we've got some of the best ideas in the world, and yet we might fail. That is thrilling. We get up every morning, this team of overachievers, people that strive to get a PhD, massive overachievers, and they're threatened every day with failure. That is a thrill. Pushing yourself to that limit and deciding whether you can do something to change society is very exciting. And Eleanor Roosevelt knew that many, many years before we came around when she said, do one thing every day that scares you. And that is what this team is doing. Now, I'll wrap this up by giving just a little bit of an update. I told you I have to take you into a deep dive. I'm going to show you some data. And I'm only going to take about 30 minutes to describe every data point here. In about 6 months, 5 computational chemists figured out the behavior of 1,800 materials, new bowling pins. Why is that important? Because all that matters to us is what's above that solid line, that bolded line. This is the idea of the ribs. We know by developing materials in the computer, 1,800 of them, the top 7 that we need to synthesize. If we'd taken that same team and gone to synthesize those materials and test them, it would have taken us 10 years. We've done the calculation. We did this in 6 months. So we are making progress, even though we're doing something that scares us because we might fail. Another version of progress is combining. You see these squiggles on the graph up here. I won't go into detail in describing them, except it is signal that comes right out of that big X-ray machine. And we've coupled that signal out of the X-ray machine with the computer so that we can actually measure now the distance between atoms of the electrolyte that solvates the ion and holds it and lets go of it when that ion moves into those bowling pins. We've used the X-ray and the computers to help us find the design space that's needed to develop an electrolyte, to go with those materials I showed you in the last slide, to develop a better battery. The team matters. Okay, now I'll finish up. In a very short time span, phones went from the Nokia indestructible brick to these iPads and all kinds of wonderful devices that connect us with the world. And what are we aiming to do? I'm bringing you back up to remind you, what is our mission? We want to deliver batteries so that everyone can drive a Tesla. And if you haven't yet, I really encourage you to do it. It's an amazing car. And it is the future of automotive transportation. We aim to have the kind of battery that will let you drive a car like that, and it'll be affordable, and let you create your own electricity and use it at will. But here's the real thing I want to leave you with. We don't know where this revolution is going to take us. We aim to deliver a cheaper Tesla and solar on everyone's rooftop with an associated battery. We do not know where it's going to bring us. And this is the case with most revolutions. And I'm going to give you just 3 examples. This is Oak Street Beach in Chicago. And in 1920, when the electricity grid was becoming prevalent and the horseless carriage was kind of moving into the mainstream, there's no way people predicted what Oak Street Beach would look like in one lifetime, 60-odd years later. An even more startling example, the Wright brothers in their first flight flew that plane for 58 seconds in 1903. 66 years later, we landed on the moon. That's almost impossible to imagine. And the best example I will leave you with is the disruption that has occurred to media. I can't imagine anyone predicting that the advent of the devices we use and the advent of the software and social media would have killed media as we knew it merely 15 years ago. As scary as that sounds, think about the opportunity. We have democratized the media. For good or for bad, we all have a voice now that is listened to. And what I would posit is if we do this right with batteries, that same democratization will occur with energy. And my point is, it's something as pedestrian as a battery that will spur this revolution. And what's underneath that is mankind's ability to understand and manipulate matter down at the atomic level to drive us to that battery. Thank you very much. And I'm sure you could experience it just by seeing that picture. I know I do. So what I'm really saying is, it's not that the revolution is coming. The revolution is here. We are tethered to a battery for our daily existence. Why? How did this happen? It's quite simple how it happened. In my lifetime, we started with a telephone that looks like the one on the left, with a dial and a wire that goes into the wall. Well, now the telephone is so much more than that. It's everything today. What would bring you to your knees in a public place? When I say that, what do you think of? A terrorist attack? A bomb going off in an airport? Smoke, fire, gunshots? What I'm here to tell you is what will bring you to your knees is what you see in this picture right here. About 3 weeks ago, I took this creep shot in the Denver airport. And I wish you could see the shots after this, the look she was giving me. There is a revolution coming. There's a revolution coming with respect to energy, how we think about, how we create, and how we use electricity in our daily lives. And I'm here to tell you about that revolution and tell you what the scientific community is doing about it so that we thrive in it. We not only survive the revolution, but that we thrive. And where I'd like to start is that word revolution. As I was thinking about putting together this talk, what images come to mind when I use that word? We think about the Bolshevik Revolution or the French Revolution or the American Revolution. And I really want you to think in your mind's eye, what does that word bring to mind? What kind of imagery? And then ask yourself, what images can apply to today if there are a revolution in our society? But if you look closely at this picture and you notice, first of all, she's trying to get some electricity to charge her battery. And look closely at the picture and you see a custodian coming by, and she has that look. We've all had that look. Yes, I'm sitting on the floor right next to a restroom charging my phone. Why? Why is that? Where is this revolution coming from? All of us have experienced the anxiety of a low battery on our phone.